Hi, welcome to the first video for Block 3, Markov Chains. This is fun stuff. So we're going to start off with discrete time Markov chains. They're a little bit easier than the continuous time ones. So first of all, what is a Markov chain? Well, if we're going to have a discrete time Markov chain, we have to have three things. First of all, a stochastic process. So a stochastic process is just some probability-based random series of events. So some process that's going to evolve over time in some probabilistic random matter. So think of some things that could be considered a random process or a stochastic process. Stuff like, what's the weather today? What's the weather tomorrow? It's somewhat random. Whether or not Natalie makes the bus, random. Other things, rolls of dice, etc., random. Okay, the second thing, the system is going to be observed at fixed time points, specific points in time. That's what makes it discrete. So one time period can be a day, it can be a month, it can be an hour, it can be 5 minutes. It just depends how you define it. The third thing is the Markovian property has to hold. So the Markovian property is kind of like the exponential distribution, which just says that the next state depends only on the current state and not on previous history. So for example, if the weather today only depends on what the weather was tomorrow and not the weather earlier this week, that would hold the Markovian property. So future state of the system only depends on the current state of the system. Okay, so if we have a stochastic process that we're observing at specific points in time as we define them, and they have this memoryless Markovian property, we have something we can model as a discrete time Markov chain. So key tenet in the middle of this is what we will define as a state. Okay, so in a discrete time Markov chain, the most challenging and important part of it is defining your states. So there are lots of different things we could look at. For example, with the weather, we could define our states as raining or not raining. We might say, okay, at 8 o'clock each morning, we're going to look at it and say, is it raining or is it not? That's our state. Now, that's a pretty limited way of looking at the weather. So more likely we have, is it raining? Is it cloudy? Is it this? Is it that? Or lots of different variables you could have there. The more states you have, the more complicated the calculations tend to get. And there are some very complex Markov chains, which you can read about in that PDF that's in the Blackboard. Anyway, so a state, another state, it can be numeric. It doesn't have to just be binary. It could be accounting. So let's say the number of ice cream sandwiches that are in my fridge. So Deb came by and said she has some to get rid of. So she put 2 ice cream sandwiches in my freezer. Now, I could say that I restock them every time I run out. So today there were 2, yesterday there were 2. Well, whether there are 2 there tomorrow only depends on today, and maybe there's some arrival rate of captains coming to snag an ice cream sandwich out of my fridge, and whoever comes first gets it. So the first 2, let's say their average arrival rate is 2 per day to come get an ice cream sandwich. And we could have states that include 2, 1, or 0 ice cream sandwiches. So in my freezer. By the way, if you're one of the first 2 cadets to show up in my office, you can have one of the ice cream sandwiches. Okay, so states. We have, within a Markov process, we're going to say that we have m+1 states because we always start with 0. The first state is always numbered as 0. Okay, so they go from 0 to m. So x of t is going to be the state of the system at time t, which is somewhere in 0 to m. So we can have x0, x1, up and so forth, up to x of m. Okay. So we have a one-step transition probability. That's the next thing. So there's some probability that you're going to go from one state to your next state in any given time. For from one time interval to the next. So what we're going to define is our one-step transition probability. We're going to call this probability that x of t plus 1, that's x of the next time, is j, given that the current state is I, whatever we define these states as. And this is going to be labeled P sub ij. So Pij is just the probability that from this time increment to the next time increment that we would go from state 1 to state I to state j. Now, if you think about it, for any given state, whatever state the system is in right now, the sum of all the transition probabilities to the possible next state, they all have to add up to 1 because something's going to happen. So even if it goes from, say, state 0 back to state 0, there's still some positive probability that we'll end up back at state 0 at the end of the time interval. Okay, now then we have this thing called the transition matrix. So the one-step transition matrix looks like this. We can take all of these transition probabilities and we can, let's say that we're going to go with m events here, or m possible states. And across this way, we're going to say here's state 0, here's state 1, all the way up to state m. Okay, so the transition probability matrix, one-step transition probability matrix is going to look like this. The probability of going from this state to that state, so the probability of going from state 0 to state 0 is going to be P00. Here we've got the P01, probability of going from state 0 to state 1. So probability if we're in state 0 at the beginning of, say, our 10-minute interval, the probability of being in state 1 at the end of our, let's say, 10-minute interval is going to be P01. And they have to add up down the column. So then we have all the way out to P0M. And then this way we have probability of going from state M to state 0, probability of going from state M to state 1, so forth, to probability of going from state M to state M. And this would be the probability of going from state 1 to state 0. Here we're going to have the probability going from 1 to 1, and so on and so forth. So this is just the probability of going from any state here to any state here. It can be 0. You can have states where you can't go directly from one into the next. Okay, so that's our one-step transition matrix. So what does it mean? Let's say that the probability of going from state 0 to state 1 is 0.5. What does that mean? Well, that means that there's a 50% probability that we're going to go from state 0, whatever that is, to state 1 in one transition, in one time interval. Okay? So, now, we can look at the world through the transition probability matrix, but it's a lot more intuitive to do this with a state diagram. So the next clip, I'm going to cover state diagrams.